In the last week, we learned about the first order linear differential equation. Sometimes we may have complex economic problems and we may have to construct differential equations of higher order. In this video, we will learn how to solve a second order differential equation. You must be familiar with this derivative. Yes, this is a second order derivative. A second order derivative means a derivative of a derivative. If an equation has a second order derivative, it is termed as a second order differential equation. The general form of a second order linear differential equation with constant coefficient and constant term is represented like this. Alpha and beta are constants. Just like first order differential equation, the solution of a second order differential equation also consists of two parts, complementary solution and particular solution. And the final solution or the general solution is the sum of the complementary solution and particular solution. To find the complementary solution, we consider the homogeneous part of the general form equation. If you can recall, the complementary solution for a homogeneous differential equation consists of an exponential part a e to the power mt. If we have a function y is equal to a into e to the power mt, then differentiating y with respect to t gives m into a into e to the power mt, and second derivative gives m square into a into e to the power mt. Now substituting the values in the homogeneous equation gives this form. Simplifying, we get a into e to the power mt within bracket m square plus alpha 1 into m plus alpha 2 is equal to 0. Note that the expression in bracket is a quadratic equation and the roots is given by using the quadratic equation formula. Thus, the roots of the quadratic equation are given by this formula. There are two interesting relationships between the two roots. First is that the sum of the roots is always equal to minus alpha 1. And second is that the product of the roots is always equal to alpha 2. Therefore, there will be two solutions of y is equal to a into e to the power mt. The complementary solution is given by the sum of the two roots, that is, yc is equal to y1 plus y2. Now we may have three cases because the roots depend on the expression under the square root. If alpha 1 square is greater than 4 times alpha 2, we have two real roots and the complementary solution is given by y1 plus y2 is equal to a1 e to the power m1t plus a2 e to the power m2t. If alpha 1 square is equal to 4 times alpha 2, both the roots are equal and the complementary solution is given by this expression. Because m1 is equal to m2 and suppose that it is equal to m. Since a1 and a2 are constants, let us consider a1 plus a2 is equal to a3. Then the complementary solution is given by the expression yc is equal to a3 e to the power mt. But we have only one arbitrary constant, hence we cannot obtain the original function from the second order differential equation. Therefore, we need another term that is independent of a3 e to the power mt. Let this term be a4 t e to the power mt. Therefore, complementary solution in this case is given by this expression. If alpha 1 square is less than 4 times alpha 2, we will have complex roots. Since this course is limited to only real numbers, we will not discuss this case in this course. Interested learners may refer to Learn More section for advanced learning. We are now left with the second part of the solution. To find the particular solution, suppose y is a constant. What is the derivative of a constant? Clearly, the first derivative and second derivative of a constant is 0. Now, this was the original equation. Therefore, we get alpha 2y is equal to beta. Simplifying further gives the particular solution as yp is equal to beta by alpha 2. The condition for this solution to exist requires alpha 2 not equal to 0. Therefore, the complete solution for the second order linear differential equation for real roots have two cases, case 1 and case 2.